Welcome back. In this video we're gonna go over number 2, worksheet 3. I'm gonna give you the full interior thought of what's going on in my head of how I figure out how to do one of these. So first, determine the final velocity of the box after it's dropped. Well, if it's dropped, we're assuming here that the velocity is going to be 0 at the beginning there. So it's just hanging out here, and then somebody lets it go from a height of 5 meters, it looks like, and it drops down there. We're going to make the system the block, and that would make most sense. We're going to include the Earth in on that, so then we can look at the potential energy of that thing. Now, you could do it without the Earth in there, but I think most people would prefer to have gravitational potential energy, which means that you have to have the Earth inside that system to have gravitational potential energy. Okay, so let's do it conceptually with the LOL diagrams, and then we'll go and figure out some of the math bits. At the beginning, we said the velocity is going to be 0, so it's going to have big fat 0 kinetic energy, but it's up high here, so it's going to have some amount of gravitational potential energy, maybe 5. We're determining the final velocity after it's dropped, and the final velocity is going to be the velocity here, like just before it reaches the ground there, the instant it touches the ground or the instant before it touches the ground. So afterwards, we know that it's not going to be high up anymore. It's going to be like right next to the ground, and we can go ahead and define our gravitational potential energy to be 0 somewhere, and right at the bottom there would make most sense. Keep going on, we go, oh hey, it lost a bunch of gravitational potential energy because now it's not as high, but as it falls down, what happens to its speed? Well, it gets faster and faster and faster, and so all of that energy must go somewhere, as energy can't be created or destroyed, and it goes into kinetic energy. All right, great. What is this telling us? Well, there's a couple ways that we could approach this problem. One is, just conceptually, what are we saying here? We're saying that all of the gravitational potential energy that was at the beginning is now going to be equal to the kinetic energy at the end there. So we could write that as 0 here and then nothing there, or some people will put like final here and they'll put like initial over here. It doesn't really matter as long as you understand that the beginning bit here is equal to the end bit over there, and that's exactly what we said. Okay, well, can we figure out any of these things? Well, we go back to our notes over there and we go, hey, gravitational potential energy, we remember that that was just mg times the h there, and so the height at the beginning there was mgh. Wait, hold on, do we have the mass of this block? Oh, there's a big oversight there. We need the mass of this block to be able to solve that. Okay, let's go ahead and let's write in the mass of the block, and you can make it up as anything that you want. I'm going to go ahead and make it 15, maybe make it 20 kilograms. All right, so mass is 20 kilograms. We know gravitational field constant there is going to be 9.8, and then the h there, it said was 5 meters. We know that that's going to be equal to the kinetic energy at the end. What is kinetic energy? Well, we found out from before that is 1/2 mv squared. So I go ahead and put that in 1/2 mv squared. Oh, now check this out. Maybe I didn't make a mistake earlier. Hey, look at that. Because now I look at this thing and I go, before I even plug in the numbers, I just write out the equation to see what's what. And then I look at both sides of the equation and go, hey, wait a second. Can I do anything mathematically? Do I have anything similar on both sides? I got a mass on both sides. Could I divide both sides by mass? Sure, it's algebraically legal. And when that happens, the mass cancels out here and the mass cancels out there. So that means that we have GH is equal to 1/2 v squared, and that's the ending velocity because it's the final kinetic energy is where that came from. Now, apparently, do we even need the mass? No, we don't. Cool. Didn't make a mistake writing that after all. So now we're trying to find for v here, so I'm going to move everything else to the other side, so I'll just multiply by 2 on both sides to get the 2 over there. So it's 2gh is equal to v squared, and get rid of the square there by square rooting both sides. So take the square root of 2gh, that's getting a little bit small there, square root of 2gh is equal to v, and now I just go ahead and put things in here. This pen doesn't work too well at the edge of the screen here, so I get the square root of 2 times 9.8 times my original height there, which was 5, And I go and calculate that. Okay, I gotta get my calculator here. 9.8 times 5 times 2, and take the square root of that. And I get 9.89. 9.8, well, it's 99. I'll write it as 99 meters per second. Cool. So that's the final velocity there. I'll maybe put a nice little circle or box around that final answer there. And that's one way to figure that out. Excellent.